again. In this lab, we're going to be looking at spectroscopy, which is one of the most useful tools that we have in astronomy. So this diagram shows an absorption spectrum from the sun. So first, let's talk about what creates this, right? So in your reading, you should have read about the electromagnetic spectrum, right? So what we're going to be looking at today is emission and absorption spectra composed of visible light, right? So of all the electromagnetic radiation spectrum, this little section here encompasses all the light that we see around us, okay? And this is between 400 or roughly 350 nanometers, I think to 775 nanometers in wavelength, right? So recall that wavelength is the distance between one wave peak to the next, right? So as we go towards shorter wavelengths, we are getting radiation that is more energetic, right? So longer wavelengths correspond to less energetic light. Okay, so for instance, red is less energetic than blue or violet light. Okay. So the second thing we need to talk about is the quantum nature of energy levels within atoms, right? So a specific identity of an atom, remember an atom is composed of a nucleus surrounded by an electron cloud, right? So the nucleus contains positive protons and neutral neutrons, right? And in surrounding them, in the part that makes up the majority of the diameter of the atom, is what is called an electron cloud, right? And the electrons in the atom are made up of, or they can have certain energies, right? And only certain energies, okay? So, for instance, this is what I'm looking for. If we were looking at a hydrogen atom, the lowest energy level is what is called the ground state. So, an electron could be found at that energy, and that is by nature, everything will seek its lowest energy state, right? However, if we have electromagnetic radiation that is incident upon this atom with an energy equal to the difference between level 2 or level 1 and level 2, then that atom can absorb that photon and jump to a higher energy level, okay? But it will only stay at that energy level for a short amount of time. When the electron falls back down to a lower energy level, it emits a photon of energy equal to the difference in energy between those two states. Okay, so if you can imagine a cloud of gas and a light incident upon that gas that is what we call an incandescent source or a continuous source, such as our sun, right? And by that we mean that in terms of visible light, it contains all wavelengths of visible light. Okay, so let's look at another example here, right? So the visible light spectrum, our sun, will emit in all of these wavelengths, right? So if there is a gas between the sun and us, a cooler gas, then the atoms within that gas are going to absorb certain wavelengths of light, right? And the wavelengths they absorb will be dependent upon the identity of the atoms within that gas, right? So it's only going to absorb wavelengths that are equal to the difference between two of these levels, okay? And when it absorbs, if we have here on Earth a diffraction grating that basically splits the incoming light into, using a prism, into this continuous spectrum, what we're going to see is holes in that continuous spectrum, right? And these correspond to the wavelengths that have been absorbed by the gas that is between the incandescent source and our receiver, right, in our spectroscope. So in that instance, we get what is called an absorption spectrum, right? So this is caused by atoms within a gas absorbing certain wavelengths of light. And we can determine what wavelengths those are and use that to identify the gas itself. At the beginning of this chapter, or this section, we see this spectrum for our sun, and this is an absorption spectrum for the gas surrounding the outside of the sun, right? So the gas emits in all visible wavelengths. However, the gases surrounding that outer part of the sun absorb certain wavelengths. So that's why we see these, you can think of them as holes in the visible spectrum. Okay. The other type of spectrum that we can get, I think there's I'm looking for a diagram. Okay, that's all right. The other type of spectrum that we can get is what is called an emission spectrum. So if we have a hot gas, then we will have a gas in which the atoms, some of the electrons within those atoms are going to be at an excited state. So a higher energy level, right? And they could be at level 2, 3, 4, 5 on up, right? But they're only going to be in that higher energy state for a limited amount of time. So when they fall back down to a lower energy, they emit a photon of light, right? And the wavelength of that photon of light is going to be equal to the difference between those two energy levels, okay? This is going to produce what we call an emission spectrum. And again, like the absorption spectrum, this is unique to the gas or the identity of the atoms that are emitting the light, right? So for instance, this is a hydrogen emission spectrum, right? So we're going to see these bars that we see, each one of these is called an emission line, and they correspond to a specific wavelength of light. So let's look at lab 3. This is 3 or 4. I think this is 4. Lab 4. Yes. Okay. So if we were in a lab, we would actually go and look at these, the spectrum of gas emission tubes. However, we're not. So I've converted this into this is just a pencil and paper lab. But you're going to look at some spectra, and you're going to identify the identity of the gas that produced those spectra. Okay, so there's 3 different parts to this. The first part, you are just looking at these 3 different types of spectra and identifying what type of spectrum that each one is, right? So remember, we have absorption, emission, and continuous, right? The second part encompasses the most of the lab. So in this one, you're going to look at 4 different sources, and you're going to evaluate this spectrum based on a couple of things, right? So you're going to look at how many lines are visible, right? First, you're going to identify the type of spectrum. You're going to count the number of spectral lines that you can see, right? So for instance, 1, 2, 3, 4. These are 2 that are close together, 5, 6, etc. And then you're going to use this scale at the bottom to estimate the wavelength of these spectral lines, right? So this goes from 700 to 600 here. So remember, this is in reverse order, so be careful. But if we look at this first violet line on this side, this is maybe about 405, 410 here. Then you're getting up toward 425, 430, something like that for this one. And then you're going to list the wavelength, the estimated wavelength of each emission line, okay, based on this scale at the bottom, right? And then you're going to look at this identity key to determine the identity of the gas, okay? So you have 4 different choices here. So for instance, helium gas would have lines at 403 nanometers, 447, 471, 492, 502, 588, and 668, right? So I know from looking at this, and I included a visible wavelength scale up here for comparison. So, for instance, in helium, we have a spectral line at 403 and 447, right? So I would expect to see some purple lines. We have some more at 447. All right, so getting more into this darker blue range. 471, we're getting into a lighter blue range. 588, right? So we're getting into a green range. And then the longest wavelength spectral line for helium would be in the 668 range, right? So that would be up here in the red range, orangish red range, right? So after you went through and kind of estimated the spectral lines of what you see here in this emission spectrum, then you're going to compare it to this identity key to identify the source that caused this spectrum, right? So there's 4 of those. In the third part, you're going to be looking at spectra that have been shifted, right? So these absorption spectra, top and bottom, are spectra for the same gas, right? So in the chapter, you should have read about something called redshift and blue shift, okay? So when something is moving really fast away from us, that causes the lines to be shifted toward the red end of the spectrum, right? So that we know that that source is moving away from us. On the contrary, on the other end, if an object is moving toward us at a high rate of speed, then its spectrum gets shifted toward the blue end of the spectrum, right? So in that case, we call it blue shifted. So we can use the spectra to identify the identity of a gas and also determine how a celestial object is moving in some cases relative to us, right? So this is what we see with distant galaxies. We see them as what is called redshifted, right? Because they are moving away from us. Okay, all right. All right, so this lab will be due on Thursday. And if you have any questions beyond this, just shoot me an email. See you guys next time.